Good afternoon, everybody. I'm Tom Wildsmith from the Offshore Renewable Energies Catapult. Welcome to our joint webinar seminar with the Royce Institute on leading edge erosion in offshore wind turbines. A couple of bits of housekeeping before we kick off. Today's session will be recorded. If you could please submit any questions using the Q&A button. We're planning to follow up after the event with the application form. If you have any technical difficulties, please let us know using the chat function. It looks like the participant numbers are sort of leveling out a little bit. So, thanks, Vicky. Yeah. So I think we're gonna start with an introduction from Dr. Steve Wyatt, our Research and Disruptive Innovation Director at the Offshore Renewable Energy Catapult. Thanks, everyone.
Good afternoon, everyone, and welcome to our workshop on leading edge erosion that we're holding jointly with the Royce Institute. I wanted to take a few moments to welcome you personally to this workshop. Thank you for giving up your time. But also, I want to set the scene a little bit, to talk a bit about the catapult and how we work, and also just set the scene for the workshop. So the Offshore Renewable Energy Catapult has been around for around 8 years now. We're here to help the acceleration and growth of great UK technology into the offshore renewable space. We have the right expertise and world-class assets that are designed to help companies de-risk their technology and move it closer to market. We measure our success on 2 key drivers: our impact in terms of reducing the cost of offshore renewable energy, and also how we are creating UK economic growth in this sector that is growing tremendously at the moment. The map on the right-hand side here gives you a sense of our regional footprint. We're headquartered in Glasgow. We have a significant testing and validation centre in Blyth, and then we're beginning to create regional offices in places like the Humber, Aberdeen, Levenmouth, and also in the southwest around Pembroke and Hale, where we see significant opportunity for things like floating wind. We're part of a bigger family. The Catapult Network has 9 technology innovation centres in sectors that are considered to be strategically important to the UK economy. We find ourselves working extensively with the High Value Manufacturing Catapult and our friends at the Energy Systems Catapult as we solve the bigger picture challenges around offshore renewables. But also, of course, emerging sectors like digital technologies are really important to what we're trying to achieve. We like to think of our role really of being one of moving technology from the left of this slide to the right of this slide, taking great ideas and concepts through the technology readiness scale towards market deployment, trying to de-risk the technology as it goes, but also working with companies to help them understand what their market potential is, how they evaluate their technology, and giving them, I guess, a mark of credibility as they move out into the marketplace to sell their products and services. I've highlighted here some of the really important emerging sectors that we're working with at the moment. So next generation technology around turbines, including things like kite power, significant activity around preventative maintenance, and particularly generally around O&M and what digital technologies and autonomous systems mean for the next generation of maintaining wind turbines, and also looking at what role the UK supply chain has to offer in the offshore renewable energy market. And increasingly, we find ourselves worrying about the variability of offshore wind. So as we have more and more offshore wind deployed, we need to think about what we do when the wind doesn't blow. So increasingly, we're working in the area of energy storage technologies, often with the Energy Systems Catapult. And of course, we don't do this alone. We like to think we fill the gap between academia and industry. So we do a lot of the translation from industry, from academia into industry. And also we help industry by understanding their challenges and try and source specific solutions. We have a number of key partners in academia. We've set up a network of research hubs in our key technology areas of rotor, powertrain, and electrical infrastructure, where we partner with the University of Bristol, the Universities of Sheffield and Warwick, and the universities of Strathclyde and Manchester. And these allow us to have really deep technical expertise that we wouldn't necessarily carry on our own payroll. We have the expertise there when we need to engage with it. That's not to say we don't work with other universities, but we find it useful to have these deep, enduring relationships. I wanted to say a little bit about the market as well. I'm sure many of you are aware around the great success story that offshore wind has been. In the next decade, government policy is set to drive the quadrupling of our industry from an installation capacity of 10 gigawatts today through to 40 gigawatts by 2030. And we've got a pretty clear roadmap where that's set out. So the graph here shows you what is operational today, then the wind farms that are under construction, those that are consented, and those that are in the pipeline for future development. So we have a pipeline of up to 50 gigawatts that we've identified, and we broadly know where it's going to be deployed. So the chart on the left here, sorry, the chart on the right here shows where the existing wind farms are today, and then where are those wind farms that are under construction and in development. And what you see is, of course, we're going further and further offshore as some of the early good close to shore sites are used up. We now find that we need longer transmission right out into the North Sea. Of course, that presents problems for maintenance. Of course, we do need even more reliable turbines to make it economic for them to operate that far offshore. So I wanted to take on a very brief tour of our facilities in Blyth. So here's an image of our 100-meter blade test facility. So this is where we can test state-of-the-art wind turbine blades. The facility is around 6 years old now, and when we built it, we thought 100 meters was huge length, and we'd never possibly need a facility that long. We're already finding that people are coming to us for inquiries for blades that are longer than 100 meters, and indeed we're having to chop the tips off blades in order to get them into our facility. It shows you the rate of progress our industry is experiencing. We also have full-scale drivetrain test facilities. So here's a picture of a 6 megawatt GE Haliade 6 megawatt turbine. That's heading into the test hall there that you can see in the background of the picture. We're delighted to have tested this machine, and now we're on to the next iteration of this turbine, which is double the capacity of this turbine. And we're also very proud of our demonstration turbine that we have off the coast of Fife in Scotland. It's a 7 megawatt turbine that allows us to demonstrate and test technologies that we wouldn't ordinarily be able to get onto a commercial wind farm. But our turbine is of sufficient scale that it's truly representative of what is happening out there in the industry today. So, for example, we're able to trial different solutions for leading edge erosion and different aerodynamic add-ons onto our blades and evaluate that technology in a very representative environment. And of course, we're here today to talk about leading edge erosion. And here's a quick snapshot. I'm sure you'll see more of this later on this afternoon. Here's a quick snapshot of our rain erosion test rig, which allows us to evaluate a huge number of samples and solutions for leading edge erosion, and also try and understand a lot more about the physics behind this. And of course, leading edge erosion is a significant problem for our sector. With wind tip speeds in excess of 100 meters per second, so that's over 200 miles an hour, cutting through the air, cutting through the saline environment, and particularly impacting the water droplets, is causing significant damage to the standard surfaces on wind turbine blades. So we need to find solutions. And it's great that we've gathered everyone here today to have this conversation and continue the search for great solutions for leading edge erosion. The economic value in finding the solutions is significant. So we estimate that 1.3 million pounds of cost savings can be achieved per turbine if we can find solutions that mean that we're not having to stop operations and send O&M teams out to repair the damage caused by rain droplets. And of course, as wind turbines get bigger, tip velocities get even higher, and this problem becomes even more of a factor. So what are we going to do today? Well, it's great that we've managed to pull together key academic partners, key members of other research institutes and industry to have this conversation and try and think about what new material solutions are out there for leading edge erosion. And I particularly want to thank our international guests for tuning in this afternoon. We're placing a particular emphasis on next generation turbines. So we're thinking about what fundamental material solutions have we got for the next generation, so we have time to develop high impact solutions for the future. And what we're really hoping for is that today we're going to identify key technology concepts, probably in the low TRL area, that the Royce Institute and the Catapult can evaluate and try and draw together into great collaborative programs that we can work on collectively in the future. Finally, I just want to end by saying a really big thank you for engaging and tuning in this afternoon. I hope you have a really productive conversation. I'm sorry I can't be there for the session. I'm actually engaged with another session looking at the recyclability of wind turbine blades, another materials challenge that I'm sure many of you have got on your radars as well. So please enjoy the afternoon, and I'll hand back to Tom. Thank you.
Excellent. So, yeah, thanks to Steve for preparing that in advance. I'd now like to ask Nick Rimmer to come on and give an introduction to the Henry Royce Institute. Nick, over to yourself.
Great. Thank you very much indeed, Tom. So I'd like to just introduce the Royce Institute, tell you a little bit about who we are, what we do. Some of you, I'm sure, are already familiar with us, but just to bring everybody up to speed. So the Royce is a national institute. We're made up of 7 different university partners and a couple of other research institutions. We're based at the University of Manchester, that's their headquarters, but we also have significant operations at the University of Sheffield, University of Liverpool, Leeds, Oxford, Cambridge, and Imperial. So a number of different locations. Pretty significant investment that was made by the UK government as about 5 years ago now was when we were founded. We've had over £235 million invested into materials science. A lot of that money has gone into facilities that we'll tell you a little bit more about later on in this presentation. So some state-of-the-art facilities that are open to researchers from across the UK. It's not an organisation where we only serve our particular universities. All of the facilities that have been set up are available to researchers, whether they're sat in industry, in academia, or even students as well. We've got access schemes for students. So range of different equipment that you'll learn a little bit more about later. In terms of what drives us, it is sustainability and the need for advanced materials to help us meet our sustainable goals. So, for example, net zero by 2050, it's a really significant challenge, given the lifetime of many of the assets, whether that be transportation equipment, whether it be wind turbines. The lifetime of these assets means that we need solutions in the next few years if we are going to be ready for 2050. Similarly, we're all aware that we've got an aging society. Healthcare is becoming more of an issue. We need to make sure we've got suitable materials available there. Similarly, around digital communications, circular economy, sustainable manufacturing, there are some really big issues that individual research organizations are unlikely to be able to solve on their own. We need to pull the material science community together to work on these challenges. In terms of the work that we get involved in, it does span across every area of material science. So everything from the atomic scale, we do work with 2-dimensional materials, the graphenes, the quantum materials, so very, very small scale, right up to very large scale. So in some of our advanced metals processing, in some of our material systems for demanding environments, some very large scale materials challenges we're looking at there as well. So range of different materials underpinned by a real expertise in imaging and characterization, so understanding the materials and the behaviors of those materials, and also a very strong digital theme as well in terms of modeling of materials and also digital approaches, digital first approaches to material science development. As I mentioned, we're made up of a number of different institutions, but in terms of what the Royce adds to those institutions, the extra that we bring is really around these 4 mission pillars. The first is kind of what we're doing today, bringing together the material science community to focus on particular challenges. We also do work around sort of understanding and documenting those challenges, sort of producing roadmaps, producing position papers that can guide funding agencies and governments in terms of where the material science community needs particular investment. I've already mentioned the facilities, and that's a big part of our day-to-day work as well, providing access to that state-of-the-art equipment that we've got spread across our various institutions. Another part of what we do, our third mission, is to support the translation of technologies out from the lab into industry. And again, I see what we're doing today as very much part of that. We're conscious that often materials developments take a long time to move from the lab, get scaled up, get qualified for use in an end application. And we're looking at ways to accelerate that, to really help that movement there. And then the fourth part of our mission is an education and outreach agenda, recognizing that material science isn't an A-level subject here in the UK. It's not necessarily an obvious subject to go into. A lot of us, certainly myself included, we kind of find ourselves material scientists after initially starting off a career in physics or chemistry or another science subject. So recognizing that there's a need to promote material science, and we do that through the Discover Materials initiative. And also we've got a strong emphasis, given our state-of-the-art equipment, a strong emphasis on providing training, technology training around the use and applications of that equipment as well. So really our activities are a lot about sort of pulling the material science community together, promoting activity, promoting material science, and getting involved in events like today, sort of whether that be an academic conference, whether it be a workshop, a whole range of different events that we organize to bring the community together around particular challenges. Now, I've mentioned several times the enormous range of equipment that we have, and at this stage I'd like to hand over to Dr. Helen Ryder, who will tell us a little bit more about some of the specific equipment that's going to be available to this project.
Thanks, Nick. So I'll just share my screen. Okay, so hopefully you can see that okay. So I'm Helen Ryder. I'm a Research and Facilities Manager for Royce at the University of Manchester, and my role is focused on imaging and characterisation. So imaging and characterisation is a cross-cutting platform that supports work across all the research areas. So the multidisciplinary characterisation facility that I manage is all about connecting and integrating multiple imaging and characterisation techniques, particularly across X-ray computed tomography, electron microscopy, surface science. So, and we offer new insights into advanced materials, and we can operate different length scales, so we're not restricted by one technique. So we also recognise the need to study the performance of materials in the demanding environments, particularly important today, so as close as possible to what they would experience in service. For example, we've got numerous in situ rigs within our facilities. Materials can be subject to things like fatigue, compression, tension, flow, temperature, heating, cooling and biasing. So just giving a little bit of an overview, an example about using multi-scale imaging in characterization across our X-ray computed tomography and electron microscopy. So this is a steel that's used in nuclear pestle vessels. We want to understand its properties and how it fails. So, and we conducted mechanical tests to evaluate toughness and the failure mechanism of that material. So, and to understand these mechanisms of failure, we've extracted some regions to analyse with XCT. So this is a non-destructive technique which allows us to create 3D and 4D images. So if you test over time and look at the changes. So, but we can use these 3D images to find region of interest. And for this particular example, these voids that form during failure, we can see these with XCT. So this provides us with really useful information. But actually, we want to look further and zoom in and understand more about the microstructure around the voids, for example. So these voids are air holes, and their X-ray committed tomography shows the hole and the metal. And when we go down in length scale with the plasma fib that we've got, it means that we're able to see these smaller voids because this is a much higher resolution technique. And so we can see that microstructure around the voids that we were looking for. And so by understanding these voids and how these voids start to grow, we can better understand the failure of these critical materials, which is really important. So that was just a very quick example, really, of how we combine some of our techniques to generate more information about what we need in materials. So Tim Burnett is in the audience today if you want to hear a little bit more about this work in correlative tomography that he does. So I also now want to move on and to highlight a few of our imaging and characterization instruments that we have available. So just taking the opportunity to talk about the latest development in our X-ray committed tomography facility in Manchester. So the NXCT is the UK's national research facility for lab-based committed X-ray committed tomography. NXCT launched in November 2020, so very new. And whilst it was investing in new CT scanning and capability, it's building on those existing capabilities and that expertise of the partners, which include Manchester, Southampton, Warwick, UCL and Diamond Light Source. And there's that real aim to deliver this unparalleled 3D imaging capability across the UK. So our NXCT hub is based at the University of Manchester, and Royce hosts all of the XCT scanners at Manchester. So where we have both cabinet-based systems and also walk-in bays. We've got a range of testing rigs that allow us to do both ex situ and in situ testing. So our systems cover a range of imaging resolutions, voxel size from 50 nanometers up to 1 millimeter for specimens ranging from 65 microns to 1 meter in length and diameter. So for example, we've got a large Rapiscan instrument, which is essentially like an airport scanner. It provides us the ability to scan large objects very fast, but the resolution is obviously very coarse with that at 1 millimeter. And then we've got our Ultra system, which is the highest resolution lab-based XCT system. As 50 nanometers, but only obviously for very fine samples with that. So our new Royce hub building will host the new visualization support center, so for the NXCT. So Royce is very much working in partnership with the NXCT and to provide that capability across the board. So looking now at our electron microscopy equipment, so we've got a huge range of EM capability across the different partners in Royce. So with SEMs, TEMs, including the STEM, these have got EBSD, EDS, EOLs, as well as in situ capability, including environmental cell holders for heating and biasing, and in situ SEM nanoindentation as well. So we have a Hysotron Pico indenter, which allows us to inform quantitative nanomechanical testing while also simultaneously imaging in the SEM as well. So coupling these two techniques allows the researcher to probe with extreme accuracy and then image that deformation throughout the test. So, which is really good. Another example of in situ capability that we have in our EM centre is the TANIST. So this is a scanning electron microscope. It really pushes those boundaries of in situ testing, particularly in the strain and temperature. And we work very closely with our equipment suppliers, with Tescan and NewTek, to co-develop the first sort of fully automated in situ testing system that can conduct the thermal and mechanical testing, as well as simultaneously undertaking the microstructural observations that you would usually expect. So in the automation that we're expected with this instrument will allow experiments to run continuously. Measurements can take place between smaller loads and temperature steps that were previously possible and over much larger range than what's possible manually as well. So very much a developmental bit of kit. We've got a resident Tescan applications engineer at the University of Manchester working on various workflows, and we're looking forward to our new TANIST instrument as well in the next month or so. The system's just arrived, we're just waiting for all the add-ins to go onto it, so that's really exciting in the sort of the next stage of that in situ testing capability that we'll have there. So just to highlight another couple of our sort of key recent purchases that we've had in terms of high-end electron microscopy. We've got the Thermo Scientific Helios 5 laser plasma fib. So this system comprises of a femtosecond laser beam, so a xenon plasma fib, and also a high resolution electron beam, which are all coincident at the same point. So the addition of this femtosecond laser to the plasma fib extends our ability to cut a wide range of samples over an even larger range of scales than we had previously. It's incredibly fast at milling, very low damage. The laser spot size is around 10 to 40 microns in diameter, depending on the conditions used. Like I say, it's a relatively recent installation to the lab. We're still getting familiar with it, but we've actually already used it to effectively cut things like graphite, aluminium, steel, nickel with a zirconium coating, resins embedded to soft tissue, etc. So the laser it does not show sort of a variability between material to material for cutting speed, but we do have to optimize, parameters when we have a new material coming in. So we've shown that the laser can produce EBSD quality surfaces for many materials, and the laser can operate serial sectioning for large 3D volumes up to 1 millimeter cubed, depending on the material. So it's going to be a really valuable tool for digging to reach the buried regions and interfaces and preparing a large array of samples and test specimens. So that's really exciting. So, and it's fitted with ultra fast EBSD and EGX detectors as well. So we've also just had a high throughput large area EBSD system, and that allows us to study a large number of samples as well, but over very large areas. So that's really great for sort of characterizing long range texture studies and investigating large numbers, say, of additive manufacturing test builds and failure analysis samples as well. So as we move on and look at what's available across our surface science area, so again, a vast range of equipment that we've got, including our mass spectroscopy imaging techniques for 3D imaging and depth profiling, with high elemental sensitivity and high spatial resolution. So for things like the nanosims, the time of flight TOF-sims, atom probe tomography. So I think Paula Robbins in the audience today, if you want to hear a little bit more about the atom probe, which sits at Oxford. So from our range of the XPS capability, just wanted to highlight the HackSpes instrument, so which is actually the world's first high throughput HackSpes lab instrument that was installed in 2019. So just by using X-rays with more than 6 times the energy of traditional XPS, the information depth has increased from several nanometers to a few tens of nanometers. So the HackSpes can probe those deeply buried layers with minimal destructive depth profiling into the bulk, and they can be applied to characterize a wide range of thin films, materials with applications, ranging from electronics to sensors, where the layer thickness and those interfacial properties are really crucial. And also the method has been shown to have that sub-monolayer sensitivity even for those deeply buried layers as well. So that's really exciting. So some of our other techniques and capability include AFM, XRD, Raman, and I just wanted to highlight our nanomechanical testing facility. This features state-of-the-art nanoindentation instrumentation. So this is designed to investigate the mechanical properties of bulk materials, coatings, polymers, even biological tissues. So the facility's got a huge range of instruments allowing for testing of these materials. Soft, is sort of tens of pascals to hundreds of gigapascals. So you sort of range from your collagen gels through to zirconium carbates coatings. So materials can also be tested in different conditions, so ambient conditions, at liquid, at set humidity, different temperatures ranging sort of from -100 to 800 degrees C. So hopefully that's given a little bit of a flavour for some of the capability that we do have across Royce, particularly, you know, sort of highlighting some of the techniques that we have available in Manchester, where I'm based. So just to let you know about accessing, so our equipment is open to all researchers for access, and we have an online database as well to find out more about what's available. So you can access that. So our info at Royce email will go to our central support team, and they will help direct inquiries to the relevant Royce partners as necessary. So it doesn't just go into a black hole, it goes to somebody who helps facilitate that out. So and they link up with our business engagement teams, our research and facility managers like myself, so who take those inquiries forward with our extensive technical teams and our academic networks that we have, who can help facilitate that access to support that test on the kit, and also supporting the designing of experiments as well. So which I think is really good. So thank you very much.
Helen, thanks for that. That's brilliant. I wish all that was available during my PhD. It would have made my life a lot easier. Right, so moving on, I would like to introduce Dr. Mark Forrest, who's going to kick off on the challenge that we're looking at around the problems and impacts of leading edge erosion.
Thanks, Tom.
While Mark's just getting ready, guys, can I just remind everyone that there's an opportunity to put questions into the Q&A box. Feel free to put them in throughout the session, and we'll try and respond as quickly as we can.
Thanks, Tom. Yeah, as Tom said, my name is Mark Forrest. I'm the Blades Research Lead at the Catapult here. Very quickly, I'd like to give an introduction to leading edge erosion in wind turbine blades from a generalist view. And then I'll hand over to Kirsten Dyer, who's our leading edge erosion specialist within the Catapult. And she'll touch upon, give an overview of the leading edge erosion science, talk about some current solutions and future requirements. And in the light of a call to action in terms of assessment of leading edge solutions going forward, she'll outline an assessment process, and then we'll take some questions. So as Steve touched upon, leading edge erosion is caused by the impingement of raindrops in the offshore environment against leading edge surfaces of blades as they operate. And it is the single largest issue for blades, both OEMs and owner operators. To go into a bit more detail from what Steve was mentioning, the two industry effects are quite large, in that continuing operation of these assets, particularly offshore. You can see the image on the right there, that the amount of erosion which can occur on the leading edge basically disrupts boundary layer flow across the blade, and this has a direct impingement upon the lift that can be produced, and therefore the torque that can be produced from the blades. And this is a direct impact on the bottom line based off the aerodynamic performance every year. So there's an obvious running reduction in a loss of revenue which occurs there as a result. But secondly, and ongoing into this issue, is the O&M cost, because obviously if these problems are allowed to mount, the accelerated damage to the asset mounts up, and obviously it has to be repaired. And so there's a fine balance between the cost required to repair these structures alongside the operating loss that we're experiencing. So every 5 years this needs to be done typically, and this is obviously recurring over the life of the turbine, which obviously is beyond 25 years. So there's significant costs which mount up to a very large extent per turbine. So basically, we need more capable material solutions to extend this limit, ideally for the life of the turbine, so that it will be zero maintenance. as far as the background in terms of showing the extent of the problem, you can see in the last 10 years, the growth of wind capacity and the number of turbines has been basically an order of magnitude increase on the number of deployed turbines offshore. And this is almost the same will occur from between now and 2050. So in terms of the numbers of turbines deployed, what is currently a problem could really hinder the industry at large. In terms of the current solutions, you can imagine these are often remote assets are operating offshore in remote, very difficult to service areas at sea, and it requires a 2 to 3 person team per turbine to actually make right, and they typically take anywhere from a few days to up to a week. The other complication of being offshore, access to the assets really goes in seasons and really go around the sea condition to even get access to the site. And so before even the costs of the direct costs of repairing these blades are incurred, just in order to get out there in terms of hire of vessels that may be required to get to the turbines is a very large cost indeed. Now typically, as I've mentioned before, the warranty periods offered by OEMs are typically around 5 years. And that has sort of spurned a large third-party market for leading-edge protection add-on kits, whether it's tapes or molded solutions to give this extra life, because there's a fine balance, obviously, between OEMs and operators of the farms, and there's mixed motivations there, because obviously on the OEM side, they'd like to reduce their capex and not necessarily put an ultimate solution, if you like, into blade leading edge erosion issues, because they want to keep costs down, obviously. But equally on the OPEX side, they're potentially losing a lot of money from materials and blades that won't necessarily perform as we would like them to be. So obviously there's a large market opportunity here for longer lived LEP solutions. So in terms of the near-term drivers, obviously the one factor which drives development in this sector is what's called the levelized cost of energy. So a metric by which we use to see that the total cost, which includes both the CapEx and OpEx, is minimum as possible. And obviously we've seen as the rise of wind energy as one of the world's cheapest forms of power, the way to access those is basically by increasing the swept area of the turbines. And that means, and this is quite obvious, because as you can see, that as the length of a blade increases, the power relationship goes to the square. So if you double the length of a blade, we're going to produce 4 times as much power. So there's obviously a physical driver to the reasons why we want to increase rotor sizes. So the current crop of state-of-the-art of 15 megawatts, we can see, there's a natural drive to go even further to the 20 plus megawatts. And the other driver, apart from the physical driver, is what's called the balance of system costs. So all those other physical assets, the costs of those physical assets like sea substructures, cabling costs, these are very, very large costs to produce a farm at sea. So obviously there's a economic driver there to have less and less turbines deployed, because the balance of system costs will decrease as a result. It's always far more economic to produce a few numbers of large turbines than a whole field of smaller turbines. So they're the 2 main drivers we want to see to try to reduce lowest cost of energy. And as you see, to go from this 15 megawatt to 20 megawatt kind of scale, we're looking at blade lengths from 100 to 120 meters. And this is where the trick is, that while the power produced is quite favorable in terms of length of a blade, the scaling of the mass of the blade as to the length isn't quite so charitable. So according to the efficiency of the blade in terms of its mass, you can see on the right hand side that different blades are more mass efficient than others, and so that exponent of that length value, the final mass can be from 2.2 up to 2.8 mass. And why is this so important? And basically it's to mitigate torque. So as the mass increases, the torque experienced by a turbine increases. So it's very much in the, and that goes with cost. So as those torque loads that we have to react out increase, the cost of a turbine increases, because drivetrain loads have to be met, as to tower, and a full consequence of cost occurs with greater mass. So it's a great driver. Now the trick is, and I think we can all appreciate this, so obviously there's the first case, we want to reduce mass regardless for efficiency, but also by reducing torque, we can get to the same equation in terms of power by increasing the speed of a turbine. So we don't have to have as large a torques experience. So to get to this efficiency apart from the mass reduction, the other way to do it is basically operate the turbine at a higher angular velocity. And obviously, as we go to higher and higher velocities, the problem of leading edge erosion amounts. But we have seen that it's projected around 3 to 5%, which is not insubstantive amounts. Reductions in the levelized cost of energy will result if we can go from a regime of 80 meters per second up to around 100 meters per second. But obviously that requires a step change in terms of the technology of the materials, but it's really an enabling approach to get to this next level of cost reductions and turbine sizes. So at the ORE Catapult, as Steve touched upon, we're looking at, we have a facility, rain erosion test rig, which uses what is the default wind industry standard rig produced by R&DAS. We use it as a commercial and research facility. So basically the idea is to get more realistic wind turbine operation and modeling of materials. So basically, as you can see there, it consists of 3 arms, which are basically a representative sample of a leading edge is placed, and that's rotated at variable speeds through a wind, this array of needles, which can simulate different offshore rain conditions. And that's used along with other tools to investigate materials, both from the science perspective as well as development of new solutions. So as a research focus, this ties into our research in terms of producing maintenance-free blades, and that's one of 3 areas. We're looking at blade remote inspection solutions. So for instance, to inspect and repair leading edge surfaces. The second obviously is blade health monitoring solutions, so we can see at what point in the life cycle of a blade those repair actions need to take place. And finally, lifetime enhancement, where we are looking at other solutions, better solutions for leading edge erosion. And with that, I'd like to hand over to Kirsten, who'll go into a bit more in depth in the science, and she'll also offer a call to action and talk about a process by which we can have materials looked at in future. Thank you, Kirsten.
Thanks, Mark. Hi, everybody. So as Mark said, I'm the leading edge erosion expert for the ORE Catapult, working in the blades team. I'm sorry. And just like a little bit of background about me is it's actually been started off in the aerospace industry a long time ago, actually, where I first came across leading edge erosion. And I've been working sort of in the topic for at least 15 years. And I'd like to turn around and say that I'm still learning as I go along. So what I'm hoping to present to you in this section is the sort of current published state of the art as I know it in terms of leading edge science, but also sort of some of the recent investigations and work that come out from the Catapult. What I'll be presenting hopefully will be used to strike your thoughts on your own technologies and what you're working on. And just to make some comments that at some points I will note where the information that I'm giving is going to be of real sort of importance in terms of the evaluation that I'll describe later on. So, just turning around. Okay, so you've already had two people define what leading edge erosion is, so I'm not going to go into it in so much detail. One of the things I did want to turn around and say is, although completely correct that rain is sort of the largest cause of leading edge erosion on wind turbines, actually it's more complicated than that. There's a load of other factors, and I'm basically going to go through and explain the factors to give you some more information. So if you look at your picture on the right of leading edge erosion, at the top, you'll turn around and see sort of some erosion on the blade. The picture on the bottom is actually the same blade 9 months later. So you can see the progress. And what we're trying to do is understand how it goes from one to the other. So the factors that have been identified as causing leading edge erosion are the wind speed, the turbine rotational speed, the blade length, the rainfall intensity, other impacting objects, weathering, chemical attack, material and system properties, and manufacturing and application. What you can turn around and see in the middle is some CFD analysis. Max already explained some of this, which is about showing you know how the wind is driving the rain into the flow of the turbine and how that resolves in terms of the sort of actual set 2D scale on the blades. So I won't go into too much detail, as I said, because Max explained it, but what's I would like to sort of show you is actually the outputs of some of the research, which is quite interesting, which turns around and shows, so on the left, if you've got a wind speed of 5 meters per second, your blade angle's at 90 degrees and your droplet size is 2 millimeter, what you can see is actually an increased intensity, shown in a slight greening on the leading edge of the turbine, but actually under the same conditions of a wind speed of 5 meters per second, same blade angle, but a droplet size of 5 millimeters, which you expect to be more damaging, you actually turn around and see that the 5 millimeter droplet doesn't actually impact the leading edge at all because of the airflow. And actually the most critical is if you've got like a 25 of those that we modeled, if you've got a 25 meters per second wind speed and a blade angle of 270 degrees and a droplet size of 5 millimeter, that causes the most extreme sort of damaging case in terms of impact energy. A little bit about droplets. So the information presented here is taken from our NOAA offshore MapMast, where we have a disdrometer installed, which is measuring sort of rainfall, but actually measuring the droplet size distributions. And this is fairly unique, that's one of the biggest issues in terms of leading edge erosion is there's a real scarcity of information about actually the sort of what are the droplet sizes offshore. So the top graph shows the precipitation intensities that are measured over the period of 1 year. And you can turn around and see that actually in this case, there were only 11 events where what we would consider as high precipitation intensity occurred. Sorry, 11 of those 11 could be classified as heavy rain or thunderstorm. That relates to a sort of a rainfall intensity of 20 to 25 millimeters per hour, and that 25 millimeters per hour has been used in aerospace as the setting of the sort of the rain erosion test requirements historically. What we're turning around and seeing is obviously there's those 11 events, and then there were 3 events of those which are actually above 80 miles an hour, which are really torrential and really damaging. In the current test method, though, what we are actually testing is 25 millimeters per hour and a 2 millimeter droplet size. I think the other thing I wanted to point out is actually the rain changes. So actually, although you can get very high precipitation intensities, what you'll see in the bottom left is actually these generally only cut for really short periods of time. So you will get a short high intensity period and then like a really low intensity period. And this is quite important because particularly when you're talking about polymeric materials, because polymeric materials can recover. The other thing to point out is obviously that your droplet sizes change dependent on your rainfall intensity. So if you see on like the bottom right, you've got like, this is a probability distribution, and this is the probability distribution measured from our offshore data. So is that the mean droplet diameter is actually around 1 millimeter and not the 2 millimeters that size that's been used in test. And actually only if you got to the extreme events would you actually come close to that 2 millimeter droplet size. So we're currently, the way we're testing is not actually representative of what's happening offshore. And so this is actually an active area of research. So other impacting objects that are often talked about, particularly hail, a lot of people have turned around and seen pictures of aircraft with large hail damage. One of our employees, while he was at Strathclyde, Hamish MacDonald, did an investigation into hail, basically taking the onshore data from UK MIDAS stations from 1949 to 2013. And what you can see is the onshore, what was recorded is the majority is ice pellets or small hail, followed by like larger hail sizes. He then converted the number of events onto a wind turbine to calculate the average annual energy. And what you can see is that the most frequent ice pellets or small hail actually has the lowest annual average energy. And it's not until you get to the slightly larger hail sizes that you're increasing in intensity, but this is still well below the intensity that is actually occurring from your rain impacts. And actually extracting from our OAREN NOAA offshore data, so we've never actually recorded any hail, and we've only recorded 6 minutes of ice pellets in 7 years with an average diameter of 1.36 millimeters. Other impacting objects that are talked about, considered important, but maybe haven't been investigated, are sand, dust, and salt spray. Sand generally is dealt with by testing to the ASTM G76 sand erosion test method. But there was a study conducted in Ireland with Suzlon, which turned around and showed that onshore, if a wind farm is located near a quarry, then actually that had the highest significant effect of erosion on turbines, which was then followed by salt on nearshore turbines. weathering, I think, is one of the key sort of critical material parameters that would be taken into consideration in terms of evaluation of new solutions. So currently, what you can see on the left is that the UVA intensity measured onshore and offshore, and these two sites are about 8 miles apart. So one's 3 kilometers offshore and the other one is just onshore. And you can turn around and see that actually the UVA intensity is 3 times as high, 2 to 3 times as high offshore. So although we're talking about degradation through rain impacts, there's obviously going to be degradation through UVA and UVB weathering impact that also needs to be taken into big account in like future solutions. Just to note in terms of temperatures and humidities offshore, so the maximum measured temperature that we've recorded is 24.7 degrees C, and the maximum humidity is 100%. The minimum temperature is minus 4.6, with a minimum humidity of 19.8, and the average yearly value shows that it's quite cold offshore. With a high humidity environment in general. So in terms of UV degradation, some of the studies that we've been doing, and this really, weathering has been really well understood by individual coatings manufacturers for decades and individual materials, but the correlation and combination of weathering with rain erosion is still a really low TRL level process. Some of the research that we have done so far has turned around, we've looked at changing color and gloss under both natural weathering and under 2 accelerated weathering test methods, QUV and sun and arc, as you can see in the left for delta E, so that's the change in color. Again, changing color and gloss is really important in terms of material solutions, as they quite often sort of can be the prevention for a solution being installed on an onshore wind turbine. Offshore, color and gloss isn't under any regulation, but onshore, local authorities set the color and gloss requirements, and if you don't meet them, your LEP won't be able to be installed. So what you can turn around and see that here we're just showing that Xenon Arc actually follows the natural weathering quite closely. Ignore the 3 measurements at the top because those are actually from a leaf falling on the surface of the sample. QUV is quite damaging, but the actual requirements after 3,000 hours is a delta E change of 1. And it's just very difficult for a lot of materials to actually meet. And that is basically because, particularly in coatings, to meet UVA requirements, people include titanium dioxide as a filler, which is sacrificial. But the titanium dioxide's presence actually affects the rain erosion performance, so it's actually a trade-off between the two. The other thing just to point out on the graph on the right is actually that after sort of natural weathering of 3,000 hours, QUV of 3,000 hours, and Xenon Arc, which are the wind industry test requirements, we're seeing absolutely no change or degradation chemically through FTIR. But these studies are continuing because at some point this it's believed that these chemical degradation is actually sudden and will occur. So it's not understood what the correlation is between accelerated weathering. So like in other corrosion tests and things like that, on the actual correlation between an accelerated test and what's really happening. Other things to consider are the humidity. So particularly in terms of polyurethane systems, which a lot of rain erosion materials are, it's actually sort of, if you're curing it in situ on a wind turbine blades, that if you're under high humidity, the resultant material might be different to what you actually have achieved and rain erosion tested in the laboratory. Temperature is usually pretty well known in terms of TG transitions and qualified by the developer. Other areas that still need to be investigated is that the coatings or product solutions could be under degradation from salt, and also acidic degradation from bugs and bird droppings, and that information has not yet been quantified. So moving on to material and system properties, and this is my favorite image for rain erosion, and this is one of those that I turn around and say is key in terms of the evaluation. George Springer, works in the US, basically developed a model based on 20 years plus of aerospace community research in terms of rain erosion. And George Springer's model turns around and says that when a droplet impacts the surface of the coating system, and what is really critical when you're thinking about your solution is in rain erosion, you're always talking about a system, not just a single LEP. And this is because as the droplet impacts, it turns around and sends a shock wave through the LEP and then onto sort of whatever is below it. So in this case, I'm showing like a classic rain erosion system, which is a coating followed by a filler or a glass epoxy. The filler could also be a gel coat. There could be a tape on top of the coating, or actually in new systems, you could actually have a hard thermoplastic or metallic actually bonded onto the glass epoxy. There's a whole range. So what you can turn around and see is obviously you're sending the shock wave through the system until it hits an interface. When it hits an interface, if the energy hasn't been absorbed by your LEP, then what you will turn around and get is a reflected wave back into your LEP system, which will doubly load the amount of stress that your LEP is seeing. The same thing goes if you have voids in the system, or if you have sort of particles, as I mentioned, like the titanium dioxide. These actually cause lots of different like little reflections and reduce the damping efficiency of the system you're creating. So what George Springer said, that the key important material properties are the acoustic impedance, the layer thickness of the LEP, the tensile and fatigue strength of your LEP, and the Poisson's ratio. These properties are used to develop a model which is used by the wind industry to turn around and predict the performance between rain erosion test rigs and wind turbines. And although it's not well validated in terms of that correlation between the test rig and the wind turbine, a lot of people have turned around and found that the theory behind this model works for their materials. So moving on to make basically more laboratory-based testing, the University of Limerick did, this was Anthony O'Carroll in his master's thesis, did a fantastic study correlating sort of different thermoplastic materials to rain erosion resistance in their rain erosion test rig. What you can see from left to right is an increasing rain erosion performance. And what you can see, first of all, is incubation time. And this is basically the time to first see some erosion damage, whereas the total duration is usually the time before you actually see the composite material. And what he turned around and found is polyethylene and polypropylene sort of have the much better like rain erosion resistance. They then compared this to nano indentation measurements. So what you would think would be important, so like your storage modulus, your loss modulus, your tan delta, and actually the relationship was found to be inconclusive. They did find some relationship with hardness, and this has also been noted by coatings manufacturers. There is seems to be some sort of relationship with hardness, where in this case lower is better. But in particular, they found that the short-term recovery, which for those who don't know, nano indentation is basically the initial depth of the nano indentation, and sort of minus the sort of almost like instantaneous recovered depth from the unloading curve. I'll come into that a bit more later, where they turn around and found that the higher the short-term recovery, the better. For ultrasonic testing, they turned around and measured the acoustic impedance and the damping ratio, and found that for thermoplastic materials, it's better to have like a lower acoustic impedance, which is saying that the sound waves are traveling through the material, and that the material, the higher damping is damping these sound waves out. They also turn around and measured mechanical properties using normal like tensile tests, so modulus, ductility, tensile strength, yield strength, and toughness, and generally found that there's a lower elastic modulus, lower tensile strength is actually better for rain erosion resistance than higher stiffnesses, higher hardnesses. And the better the ductility or the elasticity is also good. ORE Catapult have also turned around and done a similar result on metallics. This hasn't actually been published yet, where we've looked at extruded aluminium, titanium 64, and electroformed nickel cobalt. So these are all materials that are used in the aerospace industry. And their rain erosion resistance goes from aluminium at the lowest through titanium to nickel cobalt at the highest. And if we do the same looking at nano indentation, what we turn around and see is the opposite, that actually for hardness, higher is better. Short-term recovery actually matches that with the thermoplastic materials. Interestingly, the acoustic impedance in metallics is better to have a high acoustic impedance, which obviously was opposite to that in thermoplastics, and mechanical properties, better ductility, and actually higher tensile strength, which is also opposite. So what I'm trying to show from this and conclude is actually there's still a whole load of unknowns and lack of relationship between material properties and rain erosion resistance. Going back to the short-term recovery, what you can turn around and see is we've actually used nano indentation and found some correlation with short-term recovery and with what we actually observe in the rain erosion test rigs. So in this first case, we had a look at rotational speed, where we turned around and we looked at using two different rates of nano indentation. So 50 nanometers per second, and then 250 nanometers per second on the right. And if you observe the length of the arrow, to consider that as the size of the effect, the short-term recovery at the higher droplet or the higher indentation speed actually turns around and reduces the amount of elastic deformation. Same again if we look at droplet size. If we in this case, what we looked at was using different depths of nano indentation, which we assume to be equivalent to changing the droplet size. And you can also see that actually short-term recovery, as you get to a larger, what we would call droplet size, we're seeing a lower short-term recovery value. We've confirmed these very recently against rain erosion tests in a DOE, and it shows basically that the rotational speed has the highest significance for erosion, and that's great. The second next order is the droplet size. So therefore, we feel that nano indentation, if you can measure it on your material, could be a good indicator test, perhaps, of its erosion performance before it goes into the rain erosion test rig. Now moving on to the next section, which talks about what are the current solutions and what are the future requirements. So I'm going to thank Suzlan very much here. Basically, this slide was presented by Suzlan at the DTU International Symposium on Leading Edge Erosion in February this year, and shows basically a really good overview of what the current products, LEP products, are on the market. So what we can see, so the 3M products, so 3M basically have a coating system, but they're best known for their tapes, which they first started developing for aerospace and have been known for aerospace for a long time. So the current product is the W8750, but they've just introduced the new product, the 2.1. Aerox is a hybrid polyurethane urea coating system. The BASF AkzoNobel is a polyurethane coating system, as are the Mankiewicz systems, as is Hempel, as is Belzona. Technos is a polyurea coating system. The Covestro is a thermoplastic soft shield, right? We don't know the material. PPG is a coating, and then Hontek have a range of coating systems and soft shells. And then finally, Polytech is the current market leader in terms of rain erosion performance, which is a thermoplastic soft shell. So they also turned around and presented sort of an overview of the rain erosion test results. So what you can turn around and see is at the lowest, some of these products in rain erosion tests are really performing sort of like 4-5 hours, which is exceedingly low. I would turn around and say that current coating systems are sort of around your 20 to 30 hours. Of those that are on the market, and actually ones that are in development are getting higher than that. Your tape materials can perform really well in the rain erosion test, and I'll show you in a couple of slides, perform really badly on a wind turbine. But the leading product, as I said, is the Polytech L, which is LEPN. Here they show it as lasting 100 hours before failure. Ori Catapult have just finished testing, probably at a lower rotational speed, and it lasted 160 hours. Interestingly, Suzlan's comments at the bottom, are they basing their decisions only on how long the coating performs in the rain erosion test rig? And they're turning around and saying not. So they're not just looking for products that have this really high performance in the rain erosion test rig, they're also looking at how this is applied in terms of onto a wind turbine, both in production and in repair. So what's the curing time? How many thicknesses? And what general conditions are, so for currently for the sort of smaller sort of onshore wind turbines, which are sort of around your 50 meters per second, they have this rule of like production of one blade must occur in one day. So in terms of applying products that have long curing times or sort of a complicated production processes, you won't get them on. We've been told sort of by the OEMs with the bigger blades, they have a greater allowance of 3 blades. But please, when you're considering your solutions, and there is a question about application and curing times, consider that this is going to be one of the things that an OEM would assess your product by. So it's EDF also turned around and presented some of the failures. So here, a quick look, like liquid coatings, what they're turning around and seeing is that they're getting the same erosion patterns that they got on the old products, even with the new products, but it's happening in less than 5 years. I guess that the current information, which is quite sketchy, is some of the new products that I showed you on the first slide are lasting less than 1 year. And they're generally observing early failures through caused by the application process or by defects. A lot of them are failing by poor adhesion or by voids. The tapes, as you can see on the left, the tape 1.0 was the original aerospace tape, which actually had really good performance. So it lasted about 5 years of operation offshore. So that's actually probably the best recorded performance so far of any solution. The Polytech L is as yet unknown. That the 2.0 tape that they replaced it with the W8750 has actually suffered really early failures. So only after 2 years, and you can turn around and see that when it's failing, it has like a really high effect on aerodynamic on the aerodynamics. And this is something else to turn around and consider in terms of solution. As one OEM put it, if you're got a great rain erosion solution, which turns around and has more of an effect on my AEP power performance than the erosion does, I won't fit it to the turbine. The last one that I'm going to show you is the Polytech L. As I said, it's the best performing on the market. It's probably been, here they're showing a trial of 1 year, but we know of other trials where it's been on for 3 or 4 years. So far, it's not showing any signs of erosion. What they turn around and think is they'll probably get failure through the sealing of the shell on the edges. When we put this material into the rain erosion test rig, you can turn around and see that actually it does start to erode quite quickly in the test by tearing, which increases gradually. And you can see after 80 hours, the product showing significant significant damage. And we assume that at that point, or much before that point, the product would have been removed and a new shield applied. Just to turn around and say that 10 years is predicted by the Springer model to actually be 17 years on a wind turbine, to give some relationship. So what do we want from our future solutions? So the ultimate goal is to develop a solution that lasts the whole wind turbine design lifetime, 25 to 35 years, is completely maintenance free, doesn't affect the aerodynamics either on installation or as part of the erosion process, and is capable of all of this at tip speeds of 100 to 120 meters per second. Sorry, mistake. The concessions that we know the OEMs will allow on for this kind of solution against the traditional qualification requirements is removal of noise requirements for offshore only, removal of the color and gloss requirements for offshore only. The business case basically allows a high material cost solution, which they won't allow on onshore wind turbines or generic onshore wind turbines anyway. And they'll also allow this extra manufacturing time for application or integration. And so generally it's thought that these solutions, when it's developed, would be a production solution. The alternative goals are solutions that are either they're very easy and cheap to replace regularly during planned inspection periods or between inspection periods, while minimizing turbine stoppage time. So here I said possibly drone or robot solutions. Solutions that extend just beyond the current product's rain erosion performance that I've just shown you for current tip speeds. Solutions which enable high tip speeds for short periods, which are replaceable. Solutions that have better rain erosion performance or guaranteed improvement in application characteristics, and the operators are looking for those. And also one suggestion, and there might other be smart solutions. So one would be that it self-monitors, or any other smart solutions that turn around and have good rain erosion performance, but also do other things. So just coming on to the last section, which is the application process. So after this seminar, I believe an application form will turn around and be sent out to all of you. And we're asking for this to be completed by the 23rd of July. And the application form will contain the 5 questions actually shown just there. So if you have any questions on the application form, please include them either in the online section or in the Q&A section later on. So the first is to describe the material solution you're proposing and include any tensile density, speed of sound, or whether the other erosion indicative properties that I've talked about in my previous sections that have been measured. Describe the proposed approach for application of the material solution on the wind turbine, both during production and in situ repair, and if it's only one, obviously just include just the one. Describe the current development status of the material solution. Describe what further development needs to be required before it could be applied. And finally, what we're looking for is information about the main risks associated with the material solution, its application procedure and development process. So what's going to stop it coming to market, but also include things like sort of health and safety, because the wind industry, being green, has serious considerations in terms of health and safety for the materials that they use on the blades. The application forms, once they've been received, the responses will be provided by the 6th of August, so two weeks after receipt. And then the next steps will be for interesting technologies. So the ORE Catapult business development teams, that's headed up by Tom Wellsmith and others, and technical teams, including myself and Mark, will turn around and sort of work with you, where we sort of helping you with technical information. We'll support solution development, like give you reviews. This is something that's part of ORE Catapult's remit is to help bring these new technologies to market. So we're very experienced in doing that and identifying funding opportunities. And there's also, as I said, there's opportunities for testing. So as well as the rain erosion test rig, we can also do, we have some microscopy, we have some FTIR, we have outdoor weathering, and we have some supporting sort of coating tests. But actually, in terms of the majority of the materials testing, the Royce Institute, as they've described, they will support you with all of their equipment for this solution evaluation and development process. And that's me.
Excellent. Thanks, Kirsten and Mark. That's been, well, a fantastic overview of the challenge and the opportunity. There's a few questions that have come through in the chat, and I think primarily these will be, sorry, I have the fun of childcare today. Primarily aimed at Kirsten and Mark. I don't know if you've had a chance to have a look, but the first one I think is most relevant to today's call is around the test procedures for the erosion tests and the test standards. Kirsten, I don't know if you'd be able to answer that one.
Yeah, so basically, the rain erosion test, the overarching test specification is ASTM G73. There's also an ISO standard equivalent, which I believe is TS 19392-2. But the wind and the ASTM G73 was developed for the aerospace industry and is very generic. So it actually allows all types of like rain erosion test equipment and rain erosion test designs. So the all of the OEMs from the wind industry got together and developed a guideline, which is called DNV-GL RP0171, which describes the actual test procedure that they expect the rain erosion tests to be performed by. There is also a second guideline that has been issued, which I believe was free of charge, but when I looked yesterday, I'm not sure that it still is, which is DNV-GL RP0573, and that turns around and as well as giving you the rain erosion test requirements, it also turns around and tells you about the weathering and adhesion test requirements.
Thanks, Kirsten. Another one which I think sticks with the theme of today was a question here on UVA versus UVB weathering of materials, and a comment here about the Earth's atmosphere doing a lot of the absorption of UVB. One moment, everyone.
Yeah, so as well as measuring UVA offshore, we also measured UVB to really sort of understand. I think that you're correct. UVA is the most relevant, but we still get in terms of OEMs, coatings technologies in various parts of the world, but particularly in Asia, for instance, a lingering on of people sort of wanting to test to UVB. So the standard calls for UVA, but you might sometimes get asked for UVB as well.
Brilliant, thanks, Kirsten. And then Mark, there was one which came up which I wanted to pass on to you. What thermoplastic materials hold promise for rain erosion? I know you've been looking a lot at thermoplastics from a research level.
Sorry, as Kirsten showed initial ones, the olefinic systems have shown some promise, particularly the thermoplastic, particularly higher molecular weight ones, as Kirsten has shown. It's not necessarily the case, or maybe Kirsten can clarify, but I'm unaware of particularly what so-called high performance systems like your Peak can possibly do. I would say they differ somewhat, and maybe they're a outlier in a potential solution, but maybe even polyamides. I'm unaware of any testing, unless Kirsten correct me, on any pre-existing studies that have done that comparative study against the higher molecular weight polyolefins versus imides.
Yeah, so I did turn around and find not a study, a comment. So Peak has obviously shown really good performance against sand erosion. The problem to note is actually that sometimes sand erosion and rain erosion resistance are opposing. So you can't say because I've got good sand erosion, I've got good rain erosion. But I did find a comment in the US, it is available online, that Peak has exceedingly good rain erosion performance, but I've never found test results. I think that the limitations on Peak, because we have discussed with peak manufacturers is probably going to be in the weatherability.
Yeah, I mean, the whole family of aryl ether ketones, PEK, PEKK, blends with various systems, I think they all show potential promise, and usually for this kind of an application, the kind of volumes we're talking about I would say would be cost prohibitive. But as Kirsten alluded to before, the manufacturers, because it would be such an enabling technology and the problem needs to be solved, it's basically material cost, no object. Well, we won't go as far as that, but not no object, but there's a large degree of latitude in terms of cost to investigate some of these solutions.
Mm-hmm.
Brilliant, thanks both. There was a question here related to, I guess, the aim of the programme, which is to get some responses in on the application that you talked us through, Kirsten. So a question from Adam, would we be able to submit more than one questionnaire response?
Yep.
I was hoping that would be the answer.
Yes.
And there's a comment here around the extent of recovery from nano indentation tests are basically elastic recovery. So does this mean higher plasticity is bad for erosion, which probably tensile tests may show too?
It's a good question.
I would say it's firmly in the camp of not necessarily so.
Yeah.
Underscore, bold, italic, necessarily. Yeah.
So recovery is one of the very active areas of research and understanding recovery. So there's also, you have to consider there's long-term recovery and short-term recovery. Potentially both affect the rain erosion performance.
Excellent.
So, was there extra to the question?
So there's two more questions. What materials are used for blades, which is quite a generic, high-level question. So Mark, I think if you could quickly pick that one up.
Yeah, as Kirsten touched upon, there are different solutions and all respond behaviorally different according to their strengths and weaknesses. So I would say in some respects, all classes have their niche and they do things differently and they respond to rain erosion in a different way. So as Kirsten said, you may have material that's a soft material or a hard material. So they could be a metallic, or they could be an intermetallic or ceramic, a composite of either, or thermoplastic, thermoset. But how they erode is just as important. So while overall we want to keep an intact surface to limit AEP, if there's a trade-off where you can get a solution where you still don't have much erosion, but it erodes in a very gradual and forgiving way, where you're not influencing a lot of turbines. So for instance, if it can erode very evenly, you may retain a lot of AEP, for instance. So it's a hard question to answer which particular, and that's why it's such a rich field. So I think many material classes can be instituted. It's just the how and where they perform most strongly. Do you want to add anything to that, Kirsten?
No. I think you said everything really well.
Brilliant, thank you. There's a question here around blade recycling, which I know Steve picks up briefly in his introduction video. Apologies for the banging in the background. So we've got a free conference coming up on Tuesday next week on the circular economy, and we'll be hearing from two blades manufacturers, LM and Vestas, on their recycling and circular economy sustainability programs, but there'll also be some presentations from across the wider circular economy elements, so looking at, for example, recycling of rare earth materials and other components outside of just blades. But I think if you're interested in that element, that would be a good starting point. And we're also happy to discuss in more detail offline on that. We're part of SUSWIN, which is a joint industry project led by the National Composite Centre, which is very much looking at this. And we've got a couple of other research programs that we're about to kick off in this space. So it's an area we're very, very interested to talk on. There's no standards or good practices in place at this stage, but we're expecting them to sort of come out in the next few months. I'm sorry about the noise behind me. And then Kirsten, there's a follow-up question around the testing here. So this is from Adam. They have access to rebound resilience meters and DMA to monitor hysteresis. Access to a nano-indento would be a little harder. Do you think measuring the hysteresis would be a good way of measuring the short-term recovery flows without nano-indentation machines?
So in answer to your, the top level answer to your question, Adam, is yes. It's something that's been used in the past for measuring sort of some connection to like rain erosion performance. The key consideration that gets discussed, and I think what I tend to sort of I'm trying to think whether this is a sort of, I think this is something that I picked up from a lot of the reading that I've done in previous studies, impact studies, particularly impact fatigue of what we're talking about, is actually that the measured impact properties very much depend on the material that you're using for the impactor. So in terms of nano indentation, and we turn around and say we're measuring sort of, we've found this correlation with short-term recovery. Obviously in nano indentation, we're using a metallic indenter. And when you're talking about rain erosion, you're talking about a rain droplets. So the difference is a rain droplet. So not only does it cause an initial pressure on the surface, it also causes like lateral jetting along the surface as the droplet collapses. So yes, you will be able to measure it, and we are also using DMA, but just be aware that it's there's not the correlation there, known correlation at the minute. If you can send me a sort of email, I can perhaps share some more information and some more research that we're doing in that particular question, because that's also an active area.
Thanks, Kirsty. I'd be quite interested to hear from our colleagues at the Royce as well on that, given nano indentation and some of the materials analysis is very much their area of expertise. Anyone like to come in?
Yeah, I think so it's Helen, but I mean, we can certainly pass that on to the nanomechanical testing facility. So in terms of the nano indentation side, and come back to you. So it's not something I can answer today, sorry, but it is something that we would be interested in working alongside and looking at that as well. So happy to pass that over. Thanks,
Helen. So looking at the time, I think now's a good time to sort of close the event. I'd like to thank everyone for presenting and everyone for attending. I found it very interesting, still learning huge amounts around this space. As a quick reminder, we'll be sending out a follow-up, which will include sort of the questionnaire application form. We look forward to hearing some of your solutions. If there's any questions or anything else that you feel that either ORE Catapult or the Royce Institute can support you with, then please do get in touch. So yeah, once again, thanks everyone for your attendance. Enjoy the rest of your afternoons. I'm going to go and hopefully find somewhere quiet. Thank you, everyone.